Good afternoon, everyone. We're just starting today's webinar titled Identifying the Risk of a Runaway Reaction. My name is Dr. Ollie Armstrong. I'm just going to hold on for a few more minutes while some people join us. Hello again. So it's 3:03. I'll get this started. I can see most of us are here. So again, my name is Dr. Ollie Armstrong. I'm going to go through this webinar today and just tell you a little about our offering here at Sigma-HSE, but specifically today, the webinar is on identifying the risks of a runaway reaction. So the overview of today, I'm going to start with what are or is chemical reaction hazards, with some definitions and examples. Secondly, we'll say why is analysis of CRH required, what that means for your process and your developments. Thirdly, which techniques are available, so what can we use to perform that kind of analysis. And as we've got underlined at the bottom, if you have any questions as we go through today's webinar, you can drop them in the chat. We'll get back to you via email. If we've got contact details, we can set up a call. Yeah. Thank you for joining. So the objectives of today's webinar to start with. So when we're finished with this, we'd like to have a good understanding of what chemical reaction hazards are or mean and what it encompasses, how this term and study is relevant to your processes, and the techniques that we have available to ensure that any risks associated with chemical reaction hazards are properly assessed and to ensure safe chemical processes. So a little more about us at Sigma-HSE. We've got a multinational presence. We've got technical offices based in Winchester in the UK, which is where I'm speaking to you from today. We've got offices in India and in Massachusetts in the US. And we've got our two main laboratories in Winchester and in the UK and in India. So our areas of expertise, we're roughly kind of straddling that testing side of things and consultancy, with the kind of different offerings that consultancy gives. We bring together our US, UK, and Indian experts to provide our clients with EHS services and appropriate engineering solutions. And we undertake our laboratory testing in our UK labs to ISO, BSI, and ASTM standards. We do a range of sort of standard testing and sort of bespoke projects for testing as well. Our laboratory testing, which is a lot of what today's webinar will be about in terms of what we can offer. We cover the areas of chemical reaction hazards testing, thermal stability testing, powder, fire, and explosion properties, gas and vapor properties, and electrostatic properties. So the image there, quite exciting image we've got, is of a auto ignition temperature test, which is a gas and vapor test. Our consultancy services. So our consultancy team provides a wide range of specialist technical knowledge covering the following sectors: process safety management, review, DESIR and ATEX assessments, hazard HAZOP assessments, process hazard analysis, functional safety, chemical reaction hazards with COMA, training workshops, and depending on the scale of some of these, they can be performed remote on sort of desktop type studies, or there's a lot of travel for on-site work as well. So our consultants are quite busy driving around. So I'll get into the meat of my part of the presentation. So what are chemical reaction hazards? So inherent to many desired chemical reactions, which is what we're looking to do in chemistry manufacturing, inherent to that is we have undesired byproducts, quite typically. Byproducts can be in the form of exothermic and endothermic energy, as well as being byproducts in the sense of a material, an undesired material. So exothermic energy and permanent gas generation will have the highest risk potential to any process, and full knowledge of a process at scale is required to ensure safety with the process and also prevention of loss. Ultimately, when you're manufacturing, you want the most efficient process possible. That's the nature of it. Runaway reactions, unfortunately, have caused a number of industrial incidents all over the world, and we're always learning. We've got some sort of key definitions relating to thermal hazards that will sort of crop up throughout the webinar today. We've got sort of causes of overpressurization, heat of reaction, adiabatic temperature rise, the Arrhenius relationship, thermal runaway, phi factor, heat loss, and the associated changes with the scale of production or reaction, reagent accumulation, onset temperature, critically that's to do with exothermic events, and safety factors, how our tests and analysis can relate to your process at scale. And that all kind of links into how we go about doing our testing, so we make it relatable to, we're doing testing on small scale, how we make it most relevant to you guys doing reactions at large scale. So I'm sure, as you can imagine, pressure is a key hazard. Any kind of vessel which overpressurizes, you're going to either be able to slowly vent it or you're going to have an explosion. So rarely will exothermic energy or the evolution of temperature be a hazard on its own. The effects of pressure increases on a system is much more important in terms of minimizing risk. Overpressure can come from 3 potential sources in a chemical reaction: gas generation from the normal process, So you're expecting that you add A and B together, you get your product and some gas. Or gas could be your product. Number 2, so vapor pressure effects caused by heat from the normal process. And number 3, heat from the normal process, which can cause secondary reactions, decomposition, thermal runaway, which in turn generates its own gas or increased vapor pressure. So pressure effects, I just mentioned there, vapor pressure. So you've got a mass of water, and with temperature you're going to get more and more vapor in the head above it. And the natural log of the vapor pressure against temperature tends to scale linearly. So we can see on the graph here, the bottom straight bit of the green line going from right to left is temperature increasing, and it's relatively straight. This is just a typical plot. But when you combine vapor and gas pressure, so we've got this onset line here, which is indicating the generation of permanent gases, it will spike upwards away from that linear line. And that's where we get problems. So I'm just going to go through, unfortunately, a few disasters or events that have occurred over the years. And you'll see as we go through these are international over different timescales, covering different kind of processes. And this is what we want to avoid with our CRH analysis and work. So the first one is Seveso, and this was in Italy in 1976. This was a thermal runaway event where they had a reactor vessel, and due to the laws in Italy, a lot of industry will shut down at the weekends. So this was a sort of standard weekend shutdown event that went out of control. They were using steam to heat reactions. This particular reactor vessel, stirring was ceased as part of the shutdown. As other processes were also shut down, there was less demand on the heat from the steam. So what was normal heating at 190 degrees increased to about 300. With the lack of stirring, this had localized heating, which triggered a thermal runaway reaction of the reactor contents. As pressure was generated, the emergency venting system did activate, but just due to the thermal runaway reaction, it couldn't vent enough, and that there was no stirring, the thermal runaway reaction just continued. And 6 tons of these chemicals were released from the vent and settled in the surrounding area. There was no directly linked human deaths, a lot of animal deaths, and a huge cleanup operation following. So this was sort of they were kind of manufacturing disinfectants and cleaning agents in this place. We'll go through later some of the sort of common causes of runaway events. So we had the out of process occurrences here of the higher temperature, stirring was ceased, and there was also not the catches in place, such as there was no temperature reading available on the steam lines for the operators to see and react to. The next one was a horrible disaster in Bhopal in India, 1984. They had a storage tank of methyl isocyanate, which had had issues pressurizing the nitrogen head because it needed to be inert. Various issues meant that this storage vessel failed and thermal runaway reaction was initiated. They think that some water entered one of the lines and triggered the reaction. The emergency reaction systems, again, through poor maintenance and lack of investment, basically, a lot of the emergency systems weren't in place, and the whole tank was vented into the atmosphere with an incredibly high number of official immediate deaths, and you can see there the compensation that was paid to victims in the area. We can see in the picture on the right just how close they had housing nearby the plant. So coming a little bit more recently, there was an incident at T2 Laboratories in 2007. So this is in Florida in the US, a chemical reactor explosion and fire. There was a cooling system failure on a reactor, and there was no backup basically for the cooling system. And again, there was a runaway reaction. Pressure and temperature increases triggered thermal decomposition, which again meant the pressure and heat, the rate that they were being produced, increased further. Small number of deaths nearby and capital damage. But these kind of events do have a significantly bad effect on the companies. Some companies will be able to weather it. This particular company liquidated in the following months. Yeah, so again, in this case, emergency venting was activated, but it was not enough to cease the runaway reaction until the vessel exploded completely. And coming right up to date, just 2 years ago, so this was in Europe, 2021, they had some waste storage tanks, and this is still subject to investigation currently, but the thought is that some chlorinated solvents were added without the full information. They were then not subject to their storage requirement at certain temperatures. They just reached their decomposition temperatures, and there was a thermal runaway reaction, including explosion of the tank. So, as we've seen there, these kind of incidents with thermal runaway reactions can happen anywhere, quite typically where we've got chemical reactions, but also storage. If we've got chemicals that we're processing, not necessarily reacting, we need to know the thermal stability for these reasons. So this graph is from a study of where these kind of incidents occurred in industry, and we've got it right across the range, but peaking with fine chemicals and plastics. There's another survey also with the HSE, so this is a little dated now, but this kind of shows the key causes for these kind of incidents just from UK industry. So the mischarging of reactants there. We might have a system, especially with batch reactors, where we've got a tank of our main reagent and we've got a minority reagent that we may dose in small quantities. But if you can imagine that you've got a valve failure and that all adds in one go, what's the worst case of all of A plus B being added together and the kind of cooling systems you've got in place? Lack of thermochemical knowledge, so that could come under the waste storage example we've just seen. Inadequate temperature control, maintenance, agitation is a big one, and quality. Yeah. So this study in this slide is from HSE. There's also a really good HSE guidance booklet, which was authored by one of my colleagues. So this is HSG 143. And that's called Designing and Operating Safe Chemical Reaction Processes. And that covers a lot of detail that we're going through today in this webinar. So, second section, why is analysis of CRH required? And where does this kind of slot into your processes or new method developments in industry? So early on, you've got a new product identified and you're wanting to make. You're looking at potential routes to make that, and you've got a lot of desktop studies to make at that point. but you can also start looking at thermal screening. So if you're starting to identify raw materials or even the final product that you're wanting to make, then having that thermal screening information up front can sort of certainly help you make decisions. If you've got a precursor that's got a low thermal stability and you've got another candidate that is a lot more stable, then you may choose to go down route B, understandably. So you've got a chosen synthetic route optimized in this third section, and you'll probably start looking at doing some reaction calorimetry here, looking at what your heat of reactions are, your rate of reactions, and all that kind of information. It'll really help you sort of have full information of what your reaction is going to look like from a hazard point of view, and it can also help you optimize your process. What is the best agitation? What is the best heat point to do this reaction at? This stuff can all be really useful information. And it is also, when you go to the next point of scale up to plant scale and scale up to production scale, this is where you've got to have your kind of major hazards assessment. We know from the differences of scale that any kind of lab assessments of chemistry aren't going to stand up when you get to the bulk scale. And this kind of adiabatic calorimetry can help you at this point, and we'll go into why in the next few slides. And this all helps you build your basis of safety for the process. So again, this is just kind of the timeline. You've got a process and material characterization, what you want to make and what you want to make it from, how are you going to do it. Next stage, what kind of hazards you've got, identify those, what the consequences are next, and then how you design out your system to basically plan out those issues and then document it and implement. So part of the kind of desktop work you can do when you're first looking at either reagents or products, we've got certain classes of chemicals which are known to be energetic. So this just kind of helps give us, we can look at a chemical and think that maybe, yeah, that might not be so stable under higher temperatures, for example. A lot of the nitrogen groups there are quite unstable. As we all know, a lot of explosive material can have nitrogen groups. So getting on to now differences of scale. This is about how things change when we're doing a reaction on a milliliter scale, liter scale to cubes and tons, what that kind of change is, or cubic feet for the American market. As volume increases, the relative surface area decreases. So I've put this graph in here, and this is a typical plot for a cylinder. And a lot of our reactor designs are cylinder shaped typically. So we can see as the radius reduces from right to left here, you get a steep increase in the surface area to volume ratio as you're at a smaller vessel size. So basically, as you grow the volume of your reactor, you get less and less relative surface area. And typically, as you've got a reactor, the effective cooling capacity is commonly linked to the surface area of the reactor. So typically we'll have a cooling jacket on the outside of the reactor, and that is the main route to cool your reactor, which is fully surface area linked. So at the same time as we've got this effect of the differences of scale steeply increasing as you reduce the size, the heat removal capacity is typically linear, whereas the heat generation at scale is typically exponential. And we'll talk about that in the next slide. So we can see this plot here. We've got the nice dashed green line, and that is our heat removal. So if you've got a jacket on your vessel, as the temperature increases, you can only remove so much heat you've got a certain capacity on that heat removal system that no matter what you do, whether you turn the pumps up, increase the circulation, you're only going to get so much heat removal. We've got our red line, which is the heat generation due to an exothermic process. And one of the key words earlier was the Arrhenius relationship. And typically a lot of chemical reactions, the rate of that reaction will increase as the temperature increases. So this kind of causes this increasing red line. And when that red line crosses over the green line, this is where you have an excess of heat forming in the system that you cannot remove due to your normal cooling process, which is just going to build up and build up. And this is the reaction out of control being your thermal runaway. So again, some examples of differences of scale here. So we've got heat losses to the environment outside of your vessel, and they scale substantially just with the size. So this is just cooling into the environment, into air basically. We can see as the reactor size decreases from 25 cubes down to 2.5, the time that vessel takes to drop 1 degree, starting from 80 degrees, you're starting at 230 minutes for it to drop 1 degree at 25 cube. At 2.5 cube, it's just 21 minutes. So that's an order of 10 with both the reactor size and the time it takes. And then we can see at our lab scale, we might start doing these reactions in, say, a 100 ml beaker. The time it would take for that system to drop 1 degree would just be 17 seconds. You might not even notice it or measure it on your temperature profile. And then we come back to our sort of the example at the bottom, a 1 liter Dewar with less than 1 Kelvin oven. This is kind of looking at like an adiabatic test, which matches up quite well with the 25 cubic reactor. You're on the same order of time there, 245 minutes. So these kind of differences of scale, potential process deviations can only be identified with a detailed knowledge of the chemistry and the plant. And the methods available to kind of assess these hazards, HAZOPS, CHAZOPS, what-if analysis, FMEA, checklist analysis, and fault tree analysis, just to see what if anything does go wrong, what are the consequences, how can we prevent it. So you're trying to design your process towards a safe operating envelope. So that is, you're trying to provide your system with an envelope where you have your required operating temperature plus the heat of any potential exotherms, and that's got to be within your decomposition point of any anything you've got in that vessel. So that gives you your safe operating envelope. Obviously, the widest operating you can provide, it's going to be the best, and you are aiming for any small changes to the process not to have a catastrophic outcome. So we're on to now potential causes of reaction hazards. Again, like we've just been going through, improper assessment of scale-up differences. Heating and cooling requirements can vary exponentially with batch scale. How a reactor can be designed about normal operation, not worst case. So this can kind of come into the safer envelope of operation that we were just talking about. The next stage can be systems failure, so failure of critical reactor equipment or periphery services. So it can either be a failure on the cooling system on the tank or even monitoring systems external to it, but they mean that you might not be able to react to any changes. And also process failure. So that can be operator errors, incorrect information provided, that all comes under process failure. So we've got a few here which we've seen examples of. Agitator, either mechanical or power failures, and not enough performance. If you've got a highly viscous system, if you haven't got sufficient agitation, you could easily have hot zones, cool zones, and you could have thermal runaway triggered in an area, like in Seveso example, that will transition through the whole batch. But that kind of non-homogeneous system can lend itself to spot heating, which can cause an issue. On the flip side of that, coolant failure, heating failures with overheating, like the steam example, temperature, pressure, blockages, which will increase the pressure in the reflux line especially, condenser, vacuum, storage, all of these many reasons that might cause a runaway. And then process failure or system failure, I guess, incorrect reactants. That's where we were talking about before, where all of your maximum storage amounts of A and B add together, and it just overreacts. It's not normal process. Impurities, reaction of reactants with equipment, so incorrect construction materials, corrosion by reactants, that comes under the same thing, too much, too little, unexpected byproducts. This is why we should be doing CRH, so we don't have any unexpected byproducts. Reactants added too quickly, too slowly, wrong temperature, and then catalysts come into it as well, too much, too little. When you're talking about a really minority constituent like a catalyst, it's going to be easy to add too much or too little. So coming on to section 3, which is all about the kind of testing that we can provide to cover chemical reaction hazards and what we can provide for you. So there's various testing equipment and techniques available dependent on the specific process needs. So typically with this kind of work, unless our client knows exactly what they need and what they want, we will have a phone call discussion or something of the same ilk to really go through what kind of process you're working on and suggest the best route forward in terms of what testing is most appropriate. We have screening and thermal stability testing and adiabatic calorimetry testing. Coming back to the kind of size effects, I'll go into what the 5-factor is in a little time, but 5-factor needs to be considered when analyzing results. So here we are, 5-factor. So this factor provides for the relative differences between vessel sizes. As we've seen, as you scale up, cooling and heating effects react very differently depending on the size of your vessel. So this 5-factor really neatly allows you to correct for that. So heat generated in a reaction is consumed in 3 ways. That is to raise the temperature of your reaction mass. Now that's going to occur in the first instance because the heat is either the heater is in the reaction mass or you have an exothermic event in which your reaction mass is self-heating. The second consumption of heat energy is to raise the temperature of the reactor. So you've got your reactor walls, and then you have the outward transition of heat lost to the environment from your reactor walls and equipment to the environment, into the air basically. As the vessel size varies, the relative effect of reactor cooling changes also. So you can imagine as your vessel increases, you have much more reaction mass relative to the reactor and the environment, going back to that surface area ratio again. So our 5-factor is literally just a ratio of the relative mass of the sample, which is within the vessel under study. So note that heat losses are not considered. 5-factor accounts only for differences in sample to vessel sizes. So we've got some examples there. You've got a cubic glass reactor, and you've got a 5-factor there of 1.41. So that's sort of the mass and heat capacity of the container and the sample ratio. If you bump that up to a 10 cube reactor, you've got 1.13. Now, we'll talk about some of our tests. We've got the Carrier's tube screening test, which has a relatively high 5-factor of around 2.5. We've got our accelerating rate calorimeter, and we're at 1.5 5-factor at that point. And we have our pressure compensation calorimetry as an example, which is much closer to 1. Now, 1 is the best position you can be in, basically, to transfer your CRH analysis data to large-scale reactor. So 1.05 is really good. So this kind of shows the importance of the 5-factor. This is just an example plot here. We've got a high phi test with the black dotted line, and we can see over time the temperature increases studying this particular reaction, and it will not quite hold the temperature in the reaction mass in the same way that a low phi would. So you've got more heat transferring from the reaction mass into the walls of your vessel. So that is a loss of heat from your reaction system. And then you've got a low phi system with the red line, and that is holding the heat in your reaction mass. The resulting temperature is higher, and you reach this point where you have a thermal runaway and an explosion. So your high phi tests are typically good screening tests. They give you good indicative points, but you will generally have a higher sort of safety margin with any results, and you may miss events as well. So starting with screening and thermal stability. So thermal stability is a good package of data to have on its own, but we will also use a lot of these same techniques as a screening step before we move on to adiabatic or reaction calorimetry methods, just so we know what we're in for, what to expect. So these tests are typified by a low sample requirement, which is great for if you're early in your process development timeline. You might have only generated a kilo or 2 of material in the lab. So these tests, you've got a low sample requirement. You can share with us a few grams, and we can get this initial data for you. You've got speed of results. So some of these tests can be complete in 2 hours, 2 to 12 hours roughly, depending which test you go for and what the parameters are. And they will be indicative of more accurate testing. So if we find that we've got a couple of exothermic peaks, we can sort of know that in this region of temperature, when we go to a more sensitive technique, we know to look for there. So again, these are lower accuracy to large-scale systems because they have that higher phi factor. I'm not saying these are that the temperature and the pressure measurements that we take are low accuracy, because obviously all of our lab equipment is still to calibrated standards, but the data is of lower accuracy to large-scale systems. So again, these regions of interest that are found in these screening tests can be studied with adiabatic methods, requiring longer study times and greater sample amounts. So then we may move on to adiabatic calorimetry if we do find areas of interest. So these tests are typified by an increased sample requirement. Not always, but we would need in the order of 100 grams rather than 5. It's also easier to generate representative samples. So if you can imagine, you've got a reaction that requires a really minority catalyst. If we're trying to prepare a sample to go into a screening test that only requires milligrams, trying to add in exactly the right amount of catalyst is going to be very difficult. So when we scale up slightly to the adiabatic calorimetry, we're working with, tens to hundreds of grams. We can replicate the process a lot easier. So it's much more representative. We get greater accuracy results with that low phi factor, but it will have longer run times as well, which can be up to a couple of days. So again, the adiabatic definition, that heat does not enter or leave the system, so it's all about that heat in your reaction system. And this adiabatic effect in our testing can be emulated in certain ways. Okay, so differential scanning calorimetry. So DSC is a great one for really small sample amounts. We can start off with, or we can typically use sort of 5 to 10 milligrams. Really fast screening method. It can be done in 2-3 hours. It can give you a breadth of data. Specifically for us, we're looking at energetic events, but a lot of people in the plastics and glass and geology as well, they use it, so sort of studying phase transitions, morphological transitions, melting points, glass transitions. Really useful tool. So you've got a lower accuracy because we're talking about 10 milligrams a sample here, but really widely used because you've got an availability of reference data to go with your data. So this typically works, especially in our case. We've got a reference sample which should have no or will have no events as you go through the temperature ramp against your sample, and that kind of differential temperature profiles between the reference and the sample give us the plot that we provide as the data. So thermal stability is best tested in high pressure crucibles. So you've got nothing escaping. It gives you the best resolution of the signals. And like I said, the sample pan is measured against your reference pan. You've got separate heaters and separate temperature sensors. Next, I mentioned it a little earlier on, so the Kerius tube test. So the specifics of the Kerius tube, it's a small sample. This one we'd typically use about 10 grams, so it's a step up from the DSC in terms of requirement, but it's still not a huge amount. Fast testing, again, this one takes about 12 hours, and it will give you a good range of data, your energetic events, your exotherms, and also in this case, which is why we do this alongside the DSC, is we get our pressure values, and we can also infer from the data the points of where your permanent gas generation is. We can link that up with any exotherms that we see at the same time. Again, this is kind of a high phi factor test, which is why it's part of our thermal stability and screening section. So the next kind of step up we would go to, next one on Kerius tube. So the differential temperature measurements are taken basically against the oven temperature and the sample. You've got the pressure data recorded. Also, that any gases that are produced can be analyzed in line to tell you exactly what the nature is of the gases that are produced, which can be quite useful for certain processes. So you can have it hooked up to a GCMS that will tell you what your gas is as well. And from that, you can infer what your decomposition product that's left in the vessel is. And again, this is a larger sample under DSC, so it's easier to prepare a representative mix if you've got a heterogeneous sample. Our next instrument is the accelerating rate calorimetry. So for this one, it's a relatively small amount of sample, which is good. So 3 to 5 grams in a metallic bomb. We've got different grades of bomb we can use depending on the requirement. This is a slow test. It takes about 3 days. which is why we will tend to come to this if we've found something in the DSE and Carriers test. So you've got different options here as well. We can do what is called a heat weight search mode, isothermal testing, or constant ramping. So the constant ramping would be more like the DSC, and that would be a much shorter program than the heat weight search, which is what we normally use. So the heat weight search gives us in the ARC a very good adiabatic calorimetry result. Like I've got underlined there, adiabatic temperature rise is some of the data we can get out of it, and pressure generation. This is a low 5-factor test, which we showed before, typically about 1.5. And how it works basically is you have your sample in this closed bomb. You've got thermocouples in the oven all around it, and thermocouples in the vessel measuring your sample temperature. Heat weight search, how that works is it's basically stepped up, or it's programmed to step up by 5 degrees, for example, every 30 minutes, and it will dwell at that temperature, measuring the temperature of your sample, and as soon as it detects an increase in temperature of sort of 0.1 degrees, something like that, it will hold at that temperature. If it starts to detect that you've got an exotherm going on in your sample, it will increase the temperature of the oven around it, keeping it in line with your sample temperature. So that's where this comes back to being adiabatic. You're not going to get any heat loss technically from your sample because the environment is being heated to maintain that temperature. So it's a really useful tool. Moving on now to ARSST, the Advanced Reactive Systems Screening Tool. So this is another good one. It's about 5 grams of material, similar to the ARC. This one is quite adaptable as well. You can have different programs, whether that's constant ramping, heat wave search, isothermal. So this would typically be used isothermal constant ramping. So that could be in the order of 4 hours. If you wanted to do a heat weight search, that could again be days. Now this system is great for gassy decompositions or reactions that require like a nitrogen headspace, for example, just due to the design of the vessel. It's good for gassy systems. So again, it gives you a range of data, your pressure generation, and your adiabatic temperature rise, which is a key one again. This one is a great one for mid-study additions. So rather than just batching all of your reagents in one go, attaching it and setting it off, this one you can add reagents on the go, usually through a pressurized syringe. And this is a really low 5-factor system. So this is typically about 1.05. It's about as good as you can get. So we've got an example here. The reason this is good for gassy systems is that you typically run it in an open cell operation. So unfortunately, the diagram I've got is for closed cell, but if you can imagine that you've got a open glass vessel, you can pressurize the top of the containment vessel with nitrogen, which suppresses any vapor formation. So that kind of 20-25 bar nitrogen is holding something like a lid on the vessel. So that allows you to do your reagent additions. You've got your pressurized syringe to push through that headspace. And then because it is good for gassy systems, the diagram on the right with the 2 balls, your thermocouples, you can have one in your sample and one in your neck, and it can basically distinguish between foamy and non-foamy systems because the temperature profiles will be different for, crucially, that thermocouple that is in the headspace, in the neck. So you will have accompanying software that comes with the ARSST that can calculate appropriate venting for your system. So the vessel that's used is typically very thin-walled, or either glass or metal, and it is directly heated, So that gives it a very low thermal inertia cell, which goes back to the phi factor. You've got a very low mass relative to your sample mass. So next one is the VSP2. Now this is the big brother to the ARSST. They were both developed by Fauski in collaboration with the Deers group in America, and it was all about vent sizing and what kind of adiabatic calorimetry they can develop specifically for vent sizing. So this VSP2 vent sizing package 2 is basically a larger version of the ARSST. You need a larger sample required, about 70 to 100 grams. Again, the testing can be quite adaptable, what kind of program you want to run. Very similar system in terms of the you can inert the headspace or have a pressurized headspace. Range of data, pressure generation, adiabatic temperature rise. Again, you can do mid-study additions. And again, it's very low phi factor, higher accuracy to your large-scale systems. So again, this can be run in open or closed cell operation. If you run it as closed cell, it's kind of similar to the ARC in that you've got a closed system with the pressure generation. Typically, it's run as open system again. Again, the containment vessel can be pressurized to suppress any boiling or vapor generation. You've got direct heating of your vessel with a low thermal inertia vessel, very similar to the ARSST. Again, because you've got a larger sample size, it's easier to replicate addition of minority reactants or catalysts. And actually, in both of these systems, you've got good stirring, so it's easy to replicate your full-scale vessel. And finally, we've got reaction calorimetry, which is kind of the final complement to the CRH lab. So reaction calorimetry, typically a large sample, so in the order of about 200 grams. We need that kind of higher amount to make sure that we've got thermocouples and stirrers fully submersed, so it's all working correctly. Adaptable testing, so they can be sort of 8 hours to greater than 12 hours. It really depends on the reaction under study. We can normally use heat flow or power compensated modes. Again, we have mid-study additions, which are normal, and this is kind of the study of the reaction, which is based typically on an addition of A to B, which is what this system's all about. You've got a wide range of data, reaction enthalpy, adiabatic temperature rises, rate of consumption of your reagents, and you've got, again, it's a higher accuracy system. You've got a low phi factor. So reaction calorimetry, it's really adaptable. We can tack different things onto it to make it work. It can be refluxed, inerted headspace. It can be sealed up and pressurized. The data can be used to optimize your process, reduce accumulation of reactants, and investigate reaction parameter changes. So temperature, stirring, addition amounts, all that kind of stuff. The cooling jacket and heaters provide low phi data, being an adiabatic system, and it replicates actual reaction conditions. So I'll start with the power compensated calorimetry. So that uses a pre-calibrated heater. The vessel is then set to be cooled in the range of sort of 5 to 20 degrees below the desired reaction temp. The heater will then have to put in X amount of power to keep it at the desired reaction temperature. So if your system then starts to exotherm, the power needed to be input into the system to keep it at the temperature is reduced, and that's how it works out the energy output from the exotherm is basically how much or little that heater backs off to keep it at the desired temperature. So heat flow calorimetry, on the other hand, that requires calibration of your heater system and cooling system pre and post reaction to calculate accurately the heat flow. The pre and post calibrations this system will be better for if your reaction has significant changes in the liquid volume and the surface film, that cooling film where you've got the interface between your reaction mass and the cooling jacket. So any wide viscosity changes, specific heat capacity, this heat flow calorimetry is the best one to go with. So I think that winds up our kind of CRH testing webinar here. I'll just go through a summary. So we've tried to define what CRH and thermal stability are, what they mean, that pressure and temperature risks inherently come from thermal runaway reactions. We've gone through some examples of worst cases or other CRH incidents, how this links into new process considerations or alterations to a process, and what the potential causes of thermal runaway events and scale-up issues might be. Again, we've integral to the underpinning all of these, we've got the 5-factor, our kind of screening and thermal stability techniques that we can offer, adiabatic techniques, vent sizing data and how that might apply, and reaction calorimetry. So on that, thank you all very much for joining us here today. Hopefully covered some things that are of interest for you. You've got our contact details here. Any queries that you have, feel free to contact us. We'll get back to you. And this kind of webinar series, we cycle through different events through the time. If anything is of notice, just get in touch and it'll be great to talk to you. Thanks, everyone.